Hello, I am Shashank Agnihotri from University of Mannheim presenting our ECCV 2024 paper Improving Feature Stability During Upsampling, Spectral Artifacts and the Importance of Spatial Context. This is a joint work with Julia Grabinski and Professor Dr. Margret Keuper. First, let's look at the motivation for this work. Here, we see blurry images restored using the recent state-of-the-art restoration model NAFNet that, as proposed, uses pixel shuffle operation for upsampling. As shown in the first row, when blurry input is not attacked, the restoration seems decent to the human eye. However, under adversarial attack, we observe significant spectral artifacts in the restored images. These artifacts appear as repeating peaks in the frequency spectra, shown on the right. The second row shows the restoration when the pixel shuffle operation in NAFNet is replaced by a transposed convolution operation with a small kernel. Here too we observe significant artifacts both in the restored image and in the resultant frequency spectra. However, when we use our proposed large context transposed convolution for upsampling, the restored images, even under attack, have negligible artifacts appearing. This can be observed in the frequency spectra when we see no repeating peaks indicating an absence of spectral artifacts in the restored images. At this point, one might ask the question, why use adversarial attacks? To answer this, we use the following example. Here, we show an image first downsampled using max pooling and then upsampled using different upsampling operations. No adversarial attacks were used here. Here, spectral artifacts exist in the upsampled images, indicating that the network learned poor quality representations to upsample the image. However, these artifacts might not be visible to the human eye. Thus, we zoom into this very small red region and then we start observing artifacts with our human eye. Example, bilinear interpolation is causing color change and over smoothing of the features compared to the zoomed in ground truth. Whereas nearest neighbor interpolation and transposed convolution with a small kernel are both causing grid artifacts, while pixel shuffle is causing aliasing. However, the upsampling done by the large context transposed convolution is the closest to the ground truth. Thus, we show that our proposed method does hold merit even when adversarial attacks are not used. However, to ease the study, we use adversarial attacks as this accentuates the spectral artifacts exposing the inadequate learning of feature presentations by the network. Now, one might wonder what causes these spectral artifacts to occur in the first place. So, let's consider, without the loss of generality, a 1D signal I and its discrete Fourier transform f of I with k being the index of discrete frequencies. During decoding, if we upsample I to I up with a factor of 2, then for k bar equal to 0 to 2n minus 1, equation 1 equals to the following. In bed of nails sampling, I bar j is equal to 0 and thus the second term in equation 1 can simply be dropped. Now the first term resembles f of I and thus we can rewrite equation 1 using a Dirac impulse comb as the following. Such upsampling creates high frequency replica of the signal at t by 2 for t in minus infinity to infinity in f of I up, and the spatial frequencies apparent beyond array position n by 2 will be impacted by spectral artifacts if no appropriate countermeasures are taken. Below, we attempt to show this visually. On the left, we see the pink line showing linear interpolation of the samples shown in green, which in the Fourier domain causes aliasing, whereas on the right, we see that the optimal signal reconstruction is achieved by sinc interpolation. In practice, our spatial context is limited and the interpolation function is discrete. Yet, increasing the kernel size enables the approximation of larger sinc-like structures. This leads us to our hypothesis. Hypothesis 1. Large context transposed convolutions LCTC, that is, large kernels in transposed convolution operations provide more context and reduce spectral artifacts and can therefore be leveraged by the network to facilitate better and more robust pixel predictions. Our second hypothesis is the null hypothesis, which says to leverage prediction context and reduce spectral artifacts, it is crucial to increase the size of the transposed convolution kernels, that is, upsample using large filters. Increasing the size of the normal, that is, the non-upsampling convolutions in the decoder, does not have the same effect. Now, let's have a look at the method that we used to prove our hypothesis. Following is an abstract representation of an encoder-decoder architecture. While for different tasks, the implementation of the model encoder varies, including transformer-based encoders, our study focuses on the model decoder, which is shown here in green. Encoder is commonly a resonate-like structure for feature extraction. Additionally, we use convex-like structures as well. We investigate variants of different upsampling operations. The upsampling operation is shown by the red arrows in this green region. We consider as a probe for hypothesis 1 the baseline transposed convolution, and for LCTC an increased convolution kernel size, and an increased convolution kernel size with a second path using a small convolution kernel. To test whether the plain increase in parameters is responsible for the improved results, we also consider the null hypothesis. For this, we ablate on the increase in the convolution kernel size in the decoder blocks along the blue arrow in the green blocks here. As shown on the bottom right, we consider the resonate-like decoder building block structure and two convex-like structures for the backbone of the decoder. Here, we also consider an additional small convolution applied in parallel, analog to the upsampling operation here. First, we show results for the considered image deblurring task. Similar to what was observed earlier in figure 1, here we observed that our proposed LCTC significantly reduces spectral artifacts in the restored images. An increase in kernel size leads to an increase in context, and since the context is increased, the effect of uneven contribution of pixels is negated, leading to reduced spectral artifacts. This can be seen in the figure below. Here we observe that the weights for the 3x3 are high at the edges, causing the previously described grid artifacts. Whereas for 11x11 kernels, there is a smooth fading towards the border of kernels, negating this effect. Next, we show some results for the considered semantic segmentation task. Here, we observe the difference in the semantic segmentation mask predictions between LCTC and the baseline transpose convolution when used for upsampling in a unit. Green regions show where the LCTC correctly predicted the mask but the baseline failed. Red region shows vice versa, while the white regions show where both predicted correctly. Black lines are the outlines for better visual understanding. Observations made qualitatively on some samples also hold quantitatively on the entire dataset. Here, our proposed LCTC outperforms the baseline on all metrics. In conclusion, we provide conclusive reasoning and empirical evidence for our two proposed hypotheses. We show that increasing the size of convolutions upsampling, that is LCTC, increases prediction stability. We also show that increasing the size of those convolution layers without upsampling does not benefit the network. This is contrary to known literature on encoding where increasing context helped those networks, and thus we show that observations made for increased context during encoding do not translate to decoding. And lastly, we show that our proposed large context transposed convolutions can be directly incorporated into recent models, including state-of-the-art ones. Following are the references used in this presentation. For more details and experimental results, please refer to our paper. Thank you.